अच्छा जी, क्लास शुरू करते हैं. Let's start the class. So first summarize the previous lecture. So in our previous lecture we developed some expressions for the transformation of stresses. Transformation not from one point to the other point, but transformation from one orientation to the other orientation at the same point. If you know stresses in certain directions, so stress is not a vector quantity there, so that you can resolve it into its rectangular component to get stresses in some other direction. So you will have to follow the tensor rule, and these are the equations which are basically developed for the transformation of a tensor quantity, which here in this case is a stress. Okay, so we develop these expressions for the transformation of stresses, and these analytical equations, these are to calculate stresses at some inclined orientation. Okay, and these equations, they are developed to get the principal stresses and the principal plane, the plane at which the normal stresses are maximum. There will be a certain orientation at which the stresses will be maximum. And we also came to know that the stresses, the shear stresses at the principal plane are zero. So here you can see there is no shear stress at the principal plane. Sigma 1, sigma 2 are the principal stresses, and there is no shear stress. And we also develop expression for the maximum shear plane and maximum shear stresses. Okay, and here you can see the stress element where you can see the maximum stresses, and at the maximum stresses, the normal stress is not necessarily equal to zero, rather it is equal to a certain value which is sigma x plus sigma y by 2. Sigma x plus sigma y by 2 is the normal stress. Okay, and we'll discuss this one in the coming slides. So we also develop some expression between the principal and maximum shear stress plane and the corresponding stresses, and this the equation that the principal plane and the maximum shear plane always lie at an angle of 45 degrees. Okay, at an angle of the angle between the maximum shear stress plane and the principal plane is the maximum principal plane is always 45 degrees. And this is the relation how to get, if you know the principal stresses, how to get the maximum shear stress. Okay, so this expression. And then we talk about some stress and variant. There are certain quantities which remain always constant, irrespective of the orientation. If you just go from one orientation to the other orientation, but there are certain numbers, certain quantities which remain invariant, which remain constants. Okay, invariant means constant. So the first stress invariant is the sum of the stresses, sum of the two normal stresses. So if you add the two normal stresses in XY frame of reference, and if you add the two normal stresses in X prime, Y prime frame of reference, and if you add the two stresses in the principal frame of reference, then all of them will give you the same result. And this can be used as a check. Okay, you can check your result using this expression. And this is another stress invariant. This is basically tau maximum square. Okay, this is stress invariant in the XY plane, in the X prime Y prime plane, and this is in the principal planes. So for the principal plane, since shear is zero, so there is no tau component in this one. So this is simply sigma 1 minus sigma 2 by 2 whole square. And all these quantities are equal to tau maximum square. That will result in the tau maximum square. Okay. So this is the whole summary of our analytical method. Now let's do some problem. We also solve some examples. So these are the problems from your book. Okay, so problem 925. Two wooden joists 50 mm by 100 mm are glued together along the joint AB as shown in the figure. Determine the normal stress and shear stress in the glue if P is 200 kilonewton. Here you can see in this figure, this is one piece, this is another piece, and they are glued together on this inclined plane. This inclined plane is making an angle of 40 degree with the horizontal. This is making an angle of 40 degree with horizontal. Now he is saying if P is equal to, if this load is known to you, then what will be the stresses? The two component of the stresses, one will be the normal stress on this plane and the other one will be the shear stress. So to calculate those components, first you will have to calculate the stresses along the x or along the x-axis or along the xy frame of reference. Okay, because the load is given in this case is P equal to what P is in the x direction. So it will give you, obviously it will give you stress in the x direction. So each and every point of this bar is subjected to an axial stress equal to P over A, which is 200,000 divided by 15 to 100 is the area. So this is 40 megapascal. So each and every point, even this glue in x direction is subjected to this 40 megapascal stress. Okay, in this direction, but since the glue is applied in inclined direction and there is no stress in the vertical direction, sigma y is 0 and there is no shear stress in this case. So you have the state of stress defined by sigma x is 40, sigma y 0, times y 0. Okay. Now the objective is, not the state of stress is this one. This is the required state of stress. Just concentrate on this red box, red stress element, and this is the stress. So sigma x and this. So this is the only stress acting on this element in the xy frame of reference. Now the requirement is to calculate stresses along this AB plane. Now this AB plane is making an angle of 40 degree with the horizontal, with the axis of the member. But actually in the stress transformation, we required angle between the x plane and the required plane. This is our x plane and this is our required plane. Or we need angle between the x-axis and perpendicular to the required plane. This is x prime is the perpendicular to the inclined plane. Okay, so the axis, the angle between plane and plane, or the angle between x and x. So that is required. And in this case, if this is 40 degree, then this should be 50 degree. So theta 50 should be used in the transformation equation. And since this is a clockwise angle, so the angle here is minus 50 degree. Okay. Now the stress component, this is a glue direction. So the normal stress is along the glue is given by this expression. Okay. This is the transformation equation. Now if you plug in the value, the only value is this, the only stress value is sigma x and the theta. Since this is minus 50, so you will have to plug in 2 theta. So it will give you, it will result in a 16.5 megapascal stress. 16.5 megapascal stress. So in this direction, the glue is subjected to a tensile stress of 16.5 MPa. And the shear stress developed along this shear plane, along this glue, is given by this equation. So if you plug in the value, it will result in minus 19.7 MPa. Okay, and now if you want to show the result, so this is your required plane. Like you can see, this is AB. So this is this one is your required plane. So on this plane, the normal stress is 16.5 tension. And the shear stress is 19.7 negative. So negative mean counterclockwise. So here you can see on this is x prime plane. This is not x prime plane. This one is x prime plane. So this plane and this plane, you can see this is producing, the shear is producing a counterclockwise effect. So that's why if this is negative, then you'll have to show it like a counterclockwise. Now you have completed the question here because you calculated the stress component along the giant AB. But to complete the state of stress, you need also to calculate sigma y. So sigma y, you can use this equation. The only difference between sigma x and sigma y is here you have a positive sign, here you have a negative sign. Here you have a negative sign and here you have a positive sign. Okay, the sign of this first component is same. So this will result in a 23.5. So there is a tensile stress acting on this y prime plane. This is x prime. So obviously it should be y prime plane. So on the y prime plane, there is a tensile stress acting of 23.5 MPa. Okay, so this is the stress, tensile stress, and this is, so this is the complete state of stress, but the required is this 16.5 and 19.7. So you will have to design your glue, or if a number of options are available to you for glue, so you will have to select a glue which has a minimum shear strength of 19.7 and a minimum tensile strength of 16.5 MPa. Okay, so this is how you select a particular glue. Glue has these properties. When supplier provide a particular glue, so he mentioned that there's a tensile strength of this glue is this much and the shear strength of this glue is this much. Okay, so this is how you can solve a problem, a problem of practical orientation, how to get stresses in inclined plane. So this is the thing in which we talked about in our first in our previous class, that the stress 40 is the maximum stress, but this is not the design requirement. In this case, the design requirement is this 16.5 and 19.7. The stress is on this inclined plane, because you are not going to design, in this case, this may be required for the design of this wooden member, but for the design of this glue, you need these two components. Okay, so this is problem 925. And you must be able to show your stress on this element. Okay, you will have to rotate it and you will have to show it as per the sign convention. You are making a mistake in this one, so since this is not the only stress which will be acting on a body, there is a possibility that another stress may act on a body, another force may act on a body, and that could result in some stress orientation and some other stress orientation. And if you want to add these two, then the sign is very important. Okay, sign is very important. Now, next thing is a small block, 1.6 inch long, 1.2 inch high, and 0.2 inch thick, is subjected to a uniformly distributed tensile forces having the resultant values as shown in figure. Here you can see a block whose this dimension is 1.6 inch, this dimension is 1.2 inches, and the thickness which you cannot see in this view is 0.2 inches. And it is subjected to a uniformly distributed stress, uniformly distributed pressure whose resultant are given. So this is not a concentrated force. This is like a uniformly distributed force acting on this side, but its resultant is 2400 pounds. And similarly, this 1280 is a force acting uniformly distributed on this side. Okay, and this is the resultant of this force. So the question is to compute the stress components developed along the diagonal AB. This is the diagonal AB, and he is asking to calculate stresses on this diagonal AB. Okay. Now, first you will have to get the state of stress. This is not the state of stress. These are the forces. This is a finite body. This is not a differential element. So you will have to, if you pick a point from anywhere within this body, you will get the same state of stress, because this body is subjected to a uniformly distributed stress or pressure in the y direction and uniformly distribution pressure in the x direction. Okay, so it will result, obviously it will result in uniform stress condition. So if you just calculate stress in the x direction, so sigma x is equal to the force 2.4. I've written for this. Since this is, I've written it in a kip. So this is 2.4 kip divided by 1.2 into 0.2. Okay, 1.2 is this dimension, and the next 0.2 is the perpendicular dimension, which you cannot see in this view. Okay, so this will result in a 10 ksi stress, and sigma y is equal to 1.28 divided by 1.6 into 0.2. So it will result in 4 ksi. Okay. And the shear stress in this case is 0, because this in the xy plane, the shear stress is 0. Not in the other plane, but in xy plane, the shear stress is 0. Now you got the state of stress, you know the three components. You should remember this in your mind, that these three components for the stress transformation are to completely specify the state of stress at a point in plane. You need these three components. Okay. You need sigma x, you need sigma y, and you need tau xy. So they are important. Okay. But in this case, since this is basically a principal state of it, because the shear stress on this xy plane is 0, so x and y are actually the principal planes. X plane and y plane are actually the principal plane. So the angle made by now it is required to calculate stresses on in this direction. In this direction, here you can see the stress element. So you need to calculate this angle, the angle between the x plane and the required plane. Okay, so this is, you need this angle. So this angle is, if you take tangent of this theta, so tangent is 1.6 divided by 1.2. So theta is equal to tangent minus tangent inverse of this. Minus is because this is a clockwise angle. I've written it myself since I know that this is a clockwise angle. So this is minus tangent inverse of 1.6 divided by 1.2, which result in minus 53.13 degree. So this angle is how much? This angle is minus 53.13. So your theta is minus 53.13. Now these are the transformation equations. So these two components are basically required. The stress component along diagonal AB, so are these two components. So sigma x prime is equal to this one. Plug in the value 10 and 4. Okay, and theta is 53.13. So you will have to double it. So this is 106.26. So it will result in 6.16. So on the x prime plane, on this plane, the perpendicular stress is how much? The perpendicular stress is 6.16 ksi, which is a tensile stress. But the shear one, the shear stress parallel to this plane is equal to this one. Plug in the value and you will get minus 2.88 ksi. Minus 2.88 ksi is the shear stress acting parallel to this plane. Okay. Now this is, you got the answer, but if you want to complete the state of stress, okay, so you need to calculate the stress in the y direction. Okay, so y direction, the stress in the y direction, the expression is this one. Okay, so this will give you, sorry, it should be minus. It should be plus. Keep going. Okay. So here it is okay, minus and plus. It should be just distance. This is 0. It will not make a difference. It should write the proper sign. Okay. So it will result in a 7.84 ksi at tensile stress in the y direction. So this is the state of stress. Rotate the stress element by clockwise 53.13. So the stress on this direction is 6.16. This stress, shear stress, is a negative stress, so that's why it is shown as a counterclockwise stress. Okay, and the normal stress on the y plane is 7.84 ksi. Okay, positive 7.84 positive ksi. Okay, so this is the final state of stress. This is the, and this is basically the AB plane is this one, and the required stress component are 6.16 and 2.88. These are the required stress component. Okay, so calculation sometimes is very easy. Okay, you will have to just plug in the values and get the result. But to know the calculation and to know the sense of the stress, this is important. The sense of the stress, the direction of the stress, this is important. Okay, and you will have to, if you are doing a number of exercise problems, then you will be able just to clear your concept on the sign convention and on the sign of various stress components. Okay, any question? Now, this is problem 938. The state of stress at a point is the result of two separate actions. Okay. Two actions are applied on a body, and the state of stress at a point within that body is given, and obviously if two actions, so it must be the result of those two actions acting on the body. One produces now this the analysis each actions is analyzed separately. One of the action cause a pure shear of 3000 psi as shown in the figure, and it is causing stresses in the XY plane. They are causing stresses in XY plane. Okay. Now, and the other, as shown in the figure A, and the other produces the pure shear of 400,000 psi as shown in figure B. Now, here in figure B, it is rotated counterclockwise by 60 degree, and he is saying that it is causing a pure shear in this direction. Okay, the other action is causing this, the stress is in this direction. Okay. Now, find the resultant stress by rotating the state of stress in B to coincide with that in A, so that the stress can be superimposed and added directly. You cannot combine stresses if they are not in the same direction, and if they are not of the same type. You cannot add shear with the normal, and you cannot add normal with the shear. ओके, ये आप जो है वो इसको नहीं कर सकते. Now, so to combine these two, you will have to rotate this stress element so that you may get stresses in the XY plane. Okay, so first you will have to rotate this, so this is rotated in this direct in this way, so this is this plus this will give you the combined state of stress. Okay, so then determine the principal. The main objective is to determine the principal stresses and the principal plane for the combined state of stress. When you just combine both actions, then what will be the principal plane and the principal stresses? Okay, so first the state of stress, for the state of stress in case B, this is case B, the prime quantities are now known to you. Sigma x prime is known 0, sigma y prime is known 0, tau x prime y prime is 400,000. This is, since this is our x prime plane, on x prime plane they are producing a clockwise effect, so that's why it is written as a positive number. Okay, positive number. This is our x prime plane, this one is our x prime plane. Okay, so that's why this is written as a positive number. Now, required is what? To calculate the stresses in XY. So this is just an opposite kind of a problem, a reverse problem, that here the XY are unknown and X prime, Y prime are known. So these equations are this transformation equation. It can transform from XY to X prime, Y prime, and vice versa. Okay. So here, this you will have to rotate it by, the rotation will be a clockwise rotation of 60 degree. So theta, if you want to rotate from X to X, X prime to X, then you will have to use a theta equal to minus 60 degree. Since clockwise is written as a as a negative number. Okay, so this is the equation. Okay, this is the equation. Just plug in sigma x and sigma y are 0, so minus 4,000 sine of 120, which result in 3464 psi. Similarly, the shear stress on xy plane will result in minus 2000 psi, and in the y direction, the stress components are, if you just calculate the plug in the value, so you will get minus 3464 psi. Okay, so now you got the stresses corresponding to this one in the xy plane. Now you rotated this element, and this is the rotation. Sigma x is plus 3464, sigma y is minus 3464, here you can see, and the shear on this xy plane corresponding to this one is minus 5000, minus 2000. Oh, no, this is for combine, I'm sorry. Sorry. It was, okay. Okay, now you have the two stresses. One stress is this one, and the other you rotate it. So this state of stress is corresponding to this one. Now you will have to add these two state of stress. So if you add, you can add the corresponding stresses. There is no normal stress in X direction here. The only one is this one. So this is 3, 4, 6, 4. There are no normal stress in this direction. For this case, the only is this compression 3, 4, 6, 4. So you will get here 3, 4, 6, 4. Here the shear is 3000 and here the shear is 2000 and both are in the same direction. If you are making a mistake in the direction in this case, then it will not result in a 5000 stress, because then if you just reverse it, then it will result in a stress of 1000 psi, okay, which will be a wrong result. So this is the final, the combined state of stress, okay. And now the problem is simple. You will have to calculate the principal plane and the principal stresses. Okay, this is the state of stress in the XY frame of reference. So theta n is equal to this one, like in the value. Okay, so you will get 27.6 degree. It's a positive angle, counterclockwise angle. Okay, now the principal stresses are, this is the expression, sigma x plus sigma y by 2 plus minus this one, sigma x minus sigma y by 2 plus times y square. So just plug in the value, this plus minus this, so this is 0 and this is 6082. Okay, so sigma 1 is plus 6082 and sigma 2 is minus 608. Okay, now you don't know whether this angle corresponds to sigma 1 or sigma 2, so you will have to verify by plugging the value of theta n equal to 27.6 in the main expression, in the transformation expression, which is this one. Okay, so if you plug in the value in this transformation equation, I'm sorry, it shouldn't be the prime quantities, it should be, now they are in XY plane. Let me copy from somewhere else. Hang over there. Sigma n, let's call it as a sigma n, the normal stress. So the normal stress here, if you plug in the value of sigma x and sigma y, Ixy, then it will result in a 608. So it means a positive number. So this angle corresponds to 6082 to the maximum shear stress. Now show the result. So rotate the element by a counterclockwise angle of 27.6. And on that plane, this is that plane, show the positive result. If you are showing a negative result on this one, so that will be wrong. So 6082, and this is a compression of 6082. So this is the principal state of stress and along with its orientation. So the principal stress is at that point will be acting at an angle of 27.6 degree with the x-axis. Any question from your side? Now, the last topic of this analytical method is the absolute maximum shear. The maximum shear stress already discussed in this module represents the n-plane maximum shear stress. Okay. N-plane means within the XY plane, the plane which we are discussing. Okay. In the same orientation, you will have to rotate within the same plane, so that in the same plane it will give you the maximum shear stress, and this maximum shear stress is known as an in-plane maximum shear stress. The in-plane maximum shear stress may not be the maximum shear. at the point within the body, at the point within the body, it may not be the maximum shear. The shear stress may be maximum in the XZ or YZ plane. Since we are discussing the XY plane, so the other planes which are out of the direction, so out of plane, they could be XZ and YZ plane, where the shear may be maximum. The state of stress may be maybe a two-dimensional state of stress, but the state of stress may be a two-dimensional, but the shear stress may be maximum in the out of plane direction, maybe in the XZ and the YZ direction. Okay, how we'll discuss this. But that is basically if you are and the end plane may not be the maximum, so the absolute and the maximum of maximum is the absolute maximum shear stress. Okay, you get in the XY plane you get one maximum in plane shear, in the XZ plane you get one maximum in plane shear, in the YZ you get one in plane maximum shear, and then out of those three values select the maximum, so that is known as the absolute maximum value. Now, if you have, let's suppose if you have this state of stress, and this state of stress is a three-dimensional state of stress which is subjected to principal stresses. You can represent any state of stress in the form of principal stresses. Any state of stress you can represent it in the form of principal stresses. So if this is the case, and if you just look to the to this state of stress from this direction, so in this is in the 1 and 2 plane. Let me show that 1 and 2 plane. This is one direction where the stress acting is sigma 1. This is 2 direction where the stress acting is sigma 2. Now for this case, in this plane where in which this element is lying, so within this 1-2 plane, the in-plane maximum shear is given by this equation. We know that we can represent the maximum shear from this expression. We already know that we can calculate from the principal stresses, we can calculate. So this is tau 1-2. Tau 1-2 is the maximum in-plane shear in 1-2 plane. Okay, so this will be sigma 1 minus sigma 2 by 2. Similarly, if you look to this element from the top, ठीक है ना, अगर आप इसको टॉप से जो है वो देखें, so what will you see? You will see a stress element sigma 1 and sigma 3. If you are looking at it from the top, so you will see this one. So this is basically a 1-3 plane, Okay, you will see 1 and you will see sigma 2. So for this state of stress in this plane, the maximum in plane shear, which is tau 1, V is equal to sigma 1 minus sigma 3 by 2. Okay, and similarly, if you look to this this thing from this direction, from this one direction, okay, you look to this one from this one direction, okay, then you will see what? You will see a state of stress sigma 3 and sigma. You will see this case, this state of stress, and the maximum in plane shear for this state of stress is sigma 2 minus sigma 3 by 2, or sigma 3 minus sigma 2 by 2. It is not making a difference, okay, unless and until you are not adding this value to some other similar quantity. Okay, so you got this expression, you know this, and these are the stresses in a 3 dimension. Now, if you have a stress element in the two dimension, okay, so the absolute maximum for this three-dimensional element is maximum of these three values, maximum of this, and this. Now, for a two dimension, there is no sigma 3, sigma 3 is 0. If you plug in sigma 3 is 0 in this one and in this one, so it will reduce to sigma 1 by 2 and it will reduce to sigma 2 by 2. So, for two-dimensional state of stress, it will remain sigma 1 minus sigma 2 by 2. It will reduce to sigma 1 by 2 and it will reduce to sigma 2 by 2. So, you have these three values. Now, the state of stress is a two-dimensional stress, but the shear stresses are created in a three-dimension. Your state of stress is in two-dimension because you have stresses only 1 and 2. The third dimension is stress-free. Okay, this is two-dimensional state of stress. So the third dimension is stress-free, but the in-plane shear you are getting is in the other two direction also. Not in only the sigma 1 and sigma 2 plane. This is basically 1-3 plane and this is a 2-3 plane. Okay, so you are getting these three kind of stresses, and we know only this one.
Hello.
Hello, Paul. Hello.
लगा टीचर डिस्कनेक्ट हो यार.
خبري ما ولا جزار تكالكوما. سيدة ساساو. आप लोग वेट करें, नेट जरा मसला है यूपी में, और सर अभी ऑनलाइन होते हैं. Okay, sir.
आवाज राजी है साहब?
Yes, sir, Razi, sir.
Okay, so let's restart from here. So we are discussing that the in plane stress may not be the maximum stress. Okay, the out of plane could also result in the maximum stress at a certain point. So let's we are discussing an example. So let's suppose we have sigma 1 equal to 10 and sigma 2 equals to, let's suppose, minus 5. Okay, so this thing will result in 10 minus minus, so 15 divided by 2 is 7.5. This will result in 5 and this will result in 2.5. So this one will govern. Okay, the absolute maximum will be the in-plane maximum. The in-plane maximum will be the absolute maximum shear. So you can use it for, they both have different sign. If the principal stresses have different signs, then the in-plane will be the absolute maximum. Okay. Now, if you have, if they are of the same sign, okay, if they are of the same sign, like if you have sigma 1 is equal to 10 and sigma 2 is equal to 5. So it will result in 10 minus 5 divided by 2 equals 2.5. This will result in 5 and this will result in 2.5. So now the out of plane, these two are the out of plane shear stresses. Okay, so now the in plane shear stress is not giving you the maximum shear, the out of plane is giving you the maximum shear. So if they have different sign, okay, if they have different sign, then the in plane will be the absolute maximum, but if they have the same sign, then the out of plane will give you the maximum stress. Okay, so this is important. So if you are designing something for shear, then you should take care of the stresses in the other plane also. Okay, in the design of that structure element. ठीक है ना, उसको डिजाइन करने के लिए आपको उसको पूरा जो है वो you'll have to calculate the absolute maximum. The in maximum is not enough. Okay. Now let's this is the end of this module. So we discuss all the things in this case. So now we'll start our next module. Our next module is related to the stress transformation using Morse. So this is our next module, stress transformation using Morse circle. Okay. Now, the stress transformation using Mohr circle method was devised by German engineer Otto Mohr in 1882. You can imagine this is 1882, almost around about 18 plus 150 years back, almost. Okay, and you can imagine that 150 years, what will be the situation of calculations. Okay, even to multiply two number, it was a big challenge. Okay, if you have a number of, so they were devising some mechanism for the calculation. So they, in those cases, they wanted to avoid the calculation and they wanted to use some graphical representation of the things. And since it requires the stress transformation requires a lot of calculations, so Otto Mohr in 1882 devised this method of the Mohr circles.
हेलो।
जी बात हो गई है सर यार, थोड़ा वेट किया
सर
करें।
दोबारा कट गई।
तो ठीक है ना, मैंने बता दिया सर को ना। मैं किसका खुला यार, बंद करें असद महमूद।
आप मुझे सुन सकते हैं?
Yes, sir.
Okay, so we are discussing that in the Mohr circle method, a circle is drawn between normal stress and shear stress, from which stress at any orientation can be obtained. So this is basically a circle. What is the, how this is circle? What should be, for a circle you need the center location. What is the location of the center? Where it lies, and what is the radius of the circle. So these two parameters are required. If the circle is drawn to the scale, the stress can be obtained graphically from the circle usually. However, a rough sketch is drawn and results are obtained analytically using some mathematical rules or mathematical equations. Okay, trigonometric and geometric equations like the Pythagoras theorem, the sine theta, cos theta. Okay. So now to derive an expression for the Mohr circle, meaning the center and radius of the Mohr circle, which are the two requirements. So we know the stress transformation equation. This is a stress transformation equation, but I have omitted the prime word from here. So this is the stress at any orientation. Okay. This sigma is the stress at any orientation. So this is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta minus tau x y sine theta. So this implies that if you bring this sigma x plus sigma y, which is basically a stress and variance, sigma x plus sigma y is a stress and variance, so divided by 2 will also be a stress and variance. So if you bring it to the next side, so you will get this this equation, which is named as equation A. And this is the transformation of shear transformation equation, and this is equation B. Now if you square and add these equation A and B, if you square them, let's suppose if you square the right hand side, the left hand side of this equation, so this is the square plus square of the left hand side of this equation, square of the right hand side of this equation, and square of the right hand side of equation B. So this is square and adding equation A and B. So this is the left hand side is equal to, just open this, so this is A minus B. So A square plus B square minus 2AB. A square plus B square minus 2AB. आवाज तो आ रही है ना मेरी?
Yes, sir.
Okay. So here you can see A square plus B square minus 2AB. And the second one, I'm sorry, previous slide. So this is A plus B square. So this is A square plus B square plus 2AB. Now, if you look to this expression, so this one is sigma x minus sigma y by 2 square cos square 2 theta. And this one is sigma x minus sigma y by 2 square sine square 2 theta. If you combine these two, so you will get sigma x minus sigma y divided by 2 square cos square theta plus sine square theta. Okay, I have combined this one. So I have combined this one with this one. Okay? And similarly combine this one with this one. So you will get tau x square y square is equal to cos square theta 2 theta plus sine square 2 theta. Okay? And if you just look to this term and this term, so they are similar term. 2x minus y by 2 cos 2 theta, this one tau xy sine 2 theta, same but having different sign, so they will cancel. So you will get finally this expression, since this is equal to 1 and this is equal to 1, so finally you will get sigma minus sigma x plus sigma y by 2 square plus tau square is equal to sigma x minus sigma y by 2 plus tau x y square. Okay, so this is equation C. You can write this equation C in this format. This is a form of the equation. So sigma minus C square plus tau square is equal to r square. Okay, where c is equal to this one and r is equal to this one. This is a constant for a particular state of stress. This is a constant. This is the first stress invariant. And this is another constant which is represented as R, and this is another stress invariant. So these two constants are basically the two stress invariants. This is basically this term, the terms inside this square root is a stress invariant. Okay, and this term sigma x plus sigma y is the first stress invariant. So this, if you just look to this equation, so this is basically the equation of a circle. Now let me sketch a circle, a general form of the circle equation. So let me sketch a circle. So if you have a circle like this, suppose these are the x and y axis, and let's suppose this is the center of this circle. This is the center of this circle. Okay, and the coordinates of this center point are, let's suppose, A, comma, B. Meaning this distance is A and this distance is B. Okay, and if R is the radius of this circle, then what will be the equation of this circle? You know this, that the equation of this circle will be x minus a square plus y minus b square is equal to r square. This is what? This is equation of this circle. Okay, this is the standard form of equation. Now, if you have a and b equal to 0, then this equation will reduce to x square plus y square is equal to r square. This is when the center of the circle coincides with the origin of the xy plane. Okay, so this is then the equation when a and b are equal to 0. Okay, now if you just look to this one, if you look to this equation, so this equation is basically the a circle which lies like this. Let me draw this circle. So these are the xy plane and this circle is lying somewhere like this. Okay, this is the center point. This is the center of circle which is lying. If this is sigma axis, this is tau axis. Now we are now talking about the sigma, the normal and the shear stresses. So this is the center point, and the center point having coordinate of c0, where c is sigma x plus sigma y by 2, and the radius is how much? R. And R is calculating using this expression. Okay, so this is a Mohr circle. So for the Mohr circle, you need the center point, and the center point lies always on the sigma axis. Center point always lies on the sigma axis. A center point could be 0, but it could be a non-zero number. It could be a positive number. It could be a negative number. Okay, and the radius, as you can calculate the radius from this expression. So this will give you what? This will give you a circle. Okay, this will give you a circle with a known center point and with a known radius. Okay, now let's draw this circle. So this is the circle which is drawn. Here there are many things which are explained, and this thing will discuss the step-by-step development of this circle. But let's discuss some salient feature of this circle. This line and this line, they are the Cartesian coordinate x, y, and in this case the sigma and the tau line, and the intersection of these two lines is a origin, 0, 0 position. Okay, and all points on this circle, are referred to this origin. Okay, now are referring to this origin. Now, this is the origin. So you calculated the value of C. So just locate first the center point. So just take a graph paper, select the origin and the sigma and the tau plane, and then select a certain scale. Okay, select a certain scale, like you can say that 10 MPa is equal to 1 centimeter, appropriate scale, so that you can accommodate the whole circle on the available space. Okay, so you locate according to the scale, you locate the center point. So the center point of the circle here with the coordinate C0, because you are not moving in the tau direction, the y direction or the tau direction. So this coordinate is 0. So you got the center. Now open your compass according to the same scale, because you will have to select a scale, same scale for C and for R. So according to the same scale, open your compass, and with this as center, not with this as center, with this as center, draw a circle. Okay, draw a circle. So this circle is a Mohr circle. This is known as a Mohr circle. Okay. Now, each point on this Mohr circle will give you what? One will give you two coordinates. The first coordinate will be what? Will be the normal stress, and the second coordinate will be the shear stress, because the first coordinate is an abscissa, and the second coordinate is the ordinate. Okay, so this will give you the two coordinate, one as the sigma coordinate, the other one was with the tau coordinate. So each point on the Mohr circle is, since you have two planes here, you have two stress components, and on one plane in a two dimension you have two stress components. On one plane you have two stress components, one normal and one shear. So each point on the Mohr circle represent a stress plane. Like this is a stress plane, 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 this is a stress plane. Okay, each point on the Mohr circle represent a stress plane. Okay, this is one thing. Okay, we draw this, and then we are making some conclusion from this circle. Okay, now this point is the maximum normal point, because this is the rightmost point of this circle. We can discuss right. This is the rightmost point of this circle. So this point represent what? This point represent the maximum, and this is on the right side, and this is, since this is the normal, so this point is having maximum normal stress, and this point is having minimum normal stress. This is having maximum normal stress, and this is having minimum normal stress, this point. So this point and this point, they are basically the principal planes. This is the maximum principal plane. Since a point on the circle is a plane, again, a point on the circle is a plane. Okay, it represents a certain orientation. So this is the maximum point, and this is the minimum point. So these 2 points are what? These 2 points are principal stresses. Okay. Now this point is having maximum shear stress. No other point is having shear stress maximum than this one. All other points lies below this one. So this is the maximum point. So this and this is the minimum point. No other point is lying below this point. Okay. So at this point, and here you can see one thing more. Here the shear component is 0. At this point, the next coordinate comma 0, because on the sigma axis there is no tau coordinate. On the x-axis the y is always 0. Again, on x-axis the y is always 0. So if you are moving along this axis, so you will get certain value of x, but y will always be 0. Okay, so on this plane here you can see that the first coordinate is C plus R. Okay, why this is C plus R? Let's discuss it a bit later. So this point is basically, this point is the maximum shear stress and this is the minimum shear stress. Okay, now one thing I must tell you, that if you draw a radial line from the origin to a certain point, to the maximum normal plane and then to the minimum normal plane, the angle between these two lines is how much? 180 degree. Okay, 180 degree. And now the angle, this angle is from here up to here is 180 degree. In actual, the maximum normal plane and the minimum normal plane, they are perpendicular to each other. So there is one contradiction, okay, between the Mohr circle and the actual situation. Another is that the maximum shear plane and the minimum shear plane, the angle between these two planes is also 90 degree. We know this from the analytical method. So this is a 90 degree. Okay, but here once again, if you draw a radial line, so the angle between these radial line is how much? The angle between these radial line is 180 degree, double than that. Okay, so from this, and if we just plot the x-plane on this, so how to plot a certain point on this circle, okay, or how to x-plane will be a point on the Mohr circle. Okay, this is this is x-plane. You have a plane with a coordinate sigma x and tau xy. So this plane, you can get a point. So this one will be sigma x and this will be tau xy with reference to the origin. This is sigma x and this is tau xy. Okay, so this point, if you just locate the y plane, so y plane will be opposite to this one. This is y plane. Okay, so the radial line, the angle between the radial line of the x plane and radial line of the y plane is once again a 90 degree. Okay, and similar is the x prime and y prime. It is in actual it is 90, but here it is 180 degree. So we can conclude from this that the angle in the Mohr circle are double than the actual angle between the plane. The angle in the Mohr circle between the corresponding radial line is double than the angle between the respective planes. Okay, the angle between the respective plane. Okay, now so this is one conclusion. We are concluding something from this Mohr circle. One thing is that this is the maximum normal, this is the minimum, this is maximum shear, and this is minimum shear. The angle between this is 180, 180, 180. So we concluded that the angle in the Mohr circle are double than the actual angle. This is one. Okay. Now, here, since we have concluded that this is a radial line from the x-plane and this is the radial line from the principal plane, and this angle should be what? Should be double of the actual angle. This is the 2 theta and it should be 2 theta n. 2 theta n. It should be double than the actual angle between x and the principal plane. We call it as a theta n. But here it should be double than that, since in the Mohr circle the angle are double. Similarly, the angle between the x-plane and the maximum shear stress plane, we call it as a theta s, but in the Mohr circle it should be 2 theta s. It should give you double of the angle. Okay, and if you want to locate a certain plane, this is your reference. This is not your reference for the orientation. This is your reference. If you, this is x plane, so if you want to look at x prime plane, then you will have to rotate from the x plane radial line to the x prime plane through angle of 2 theta. Not theta, 2 theta, because in the Mohr circle the angle is always double than the angle between the actual plane. Okay, so you will have to rotate by 2 theta. So this is all about this Mohr circle. And let's now talk about these some other point also, that if this is having coordinates, so it is a zero coordinate, so meaning that the shear stress at this point is zero, so it should be the principal plane. And here the normal stresses are same, C and C. C and C. It should have a C coordinate because you are moving this from here up to here is C, and from here up to here, since this is radius, so it should be R. Okay, this distance is R. Okay, so now you got this. So maximum shear stress plane, minimum shear stress plane, principal plane, X, Y orientation, and all these things. Then how to draw a Mohr circle? So this is the step-by-step procedure. A step-by-step procedure to draw a Mohr circle.
सर
जी
सर ये की कोई रीजन है या वैसे ही
क्या
टू थीटा जो है इसकी जगह अगर थीटा
there is a reason if you just look to the equation from which we got these expression. Okay, these expression involve 2 theta, which omitted in this whole process, but actual transformation involved not the theta angle, it involves a 2 theta. Okay, so that's why, since this is a tensor quantity and tensor quantity is related to the linearly to the 2 theta number, not to the theta number, so that's why in the Mohr circle it is also a 2 theta. ठीक है ना? So ये इसका जो है वो रीजन ये है कि इसका बैकग्राउंड जो है वो 2 थीटा पर बेस है. ठीक है? Okay जी. So this is a step-by-step procedure to draw a Mohr circle. So first you will have to do what? You will have to, for the given state of stress, you will have to calculate the center and the radius. Even I'll tell you later on that you can avoid even to calculate C and R value because it requires also a lot of calculation. So without calculation, you can draw a Mohr circle. Without calculating the C and the R value, you can draw a Mohr circle. We'll talk about this later on. But for a routine procedure, so you will have you calculate a C and you calculate R. आप C और R calculate करते हैं. ठीक है ना? So when you just calculate C from this expression or from this expression. Now selecting appropriate scale, appropriate mean according to the available space with you. Locate center and draw Mohr circle of radius. So you know the C, so just locate this point, the center point. So you can easily locate. You will have to move to this side by through amount of C according to the scale. With this as center, open your compass equal to R according to the same scale and draw this circle. Okay, so this is the circle. Then the next step is write coordinates of principal plane and maximum shear plane. You can write these coordinates. So this is C plus R. So this is the principal plane, maximum normal stress plane. This is minimum normal stress plane. Both of them are principal plane. Okay, so C plus R and 0, C plus R minus 0. Okay, why this is C plus R? They can C and this is R because this is the radius of the circle. So this is C plus R and this is C minus R. This is R minus C, but since you are on the opposite side, so it should be C minus R. And there is always also a possibility that C could be higher than R value. So it will automatically control the sign if you are using C minus R. Okay, so C minus R. Okay, C can be a positive or a negative value, and R is always a positive number. Okay, so the center could be on this negative side also. Again, ज़रूरी नहीं है कि positive side पर हो. So these are the coordinates of the principal plane, and since this is this x coordinate or this sigma coordinate is C, so this point should also a sigma coordinate of C, and the tau coordinate should be equal to R because this distance is equal to R. So C plus R, and similarly for this is C minus R. So you draw to calculate the C and R, you draw the Mohr circle and you just write the coordinates of this, and this point. Okay, so this is a kind of a first stage, okay, where you draw the Mohr circle. The next is you will have to locate the x plane on the Mohr circle. Okay, how to locate the x-plane. So just how you point, how you locate a point on the graph. Okay, so you just take on x-axis, on sigma axis, just come equal to sigma x, and on y-axis just move equal to tau xy. It could be a positive or a negative depending upon the sign of these stresses. Okay, so just move from this, not from this distance from here up to here, this is sigma x, and from here up to here, this is tau xy. So then you will get this point automatically. These two lines should intersect on this circle. If they are not intersecting on this circle, then there will be some problem in your whole procedure. Okay, it should intersect on this circle. So you need just one line. You just take, let's suppose, tau xy and draw this line, so it will intersect the circle and draw this line. So just sigma x, draw this vertical line, so it will intersect the circle and draw this. So just one of them is required, the other one will automatically you will get there. So this is now the x-plane. Okay, this is the x-plane. If you join this point, since I've told you that a point on the Mohr circle is a plane, is a stress plane. So this is a point on the Mohr circle, and this particular point represents the x-plane. Okay, join this with the center and extend it on the back side, so it will intersect the circle on this y-plane. You cannot. This will automatically intersect, so you need not to do you need not to locate it. It will automatically be located. It should give you automatically that its x coordinate will be sigma y and its y coordinate will be minus y automatically. Okay, so you need just to locate the x1 and join this with the center, not with the origin. Remember, not with the origin. I am repeating. Okay, join with the center of the circle and extend it on the next on the opposite side, so you will get this y. Okay, next. When you just locate the x-plane, so now you can locate the principal plane with respect to the x-plane. Since you know the principal stresses, but you don't know what is the location of the principal stresses. Okay, what is the location of the principal? Because the location of the principal plane should be with reference to the x-plane, not with reference to the sigma and these things, with reference to the x-plane. Okay, so as we know that the angle in the Mohr circle are double, so this is a radial line from the x-plane and this is a radial line from the principal maximum stress. So this angle will be 2 theta. Okay, and from a very simple trigonometric relation, if you just take sine of 2 theta, so this will be equal to this, which is tau xy divided by r, which is the radius of this circle. This is what r, and this is why I have to exclude, you will have the sign, because this is automatically giving you the sign that the principal plane is lying at a clockwise angle. Again, at a clockwise angle. This is automatically giving you, when you draw a circle to the scale, so it will automatically give you, it will be on this side. Okay, so this is 2 theta, so this will give you the value of theta, and if knowing the value of 2 theta, you can get the value of 2 theta, because in this sometimes if the line is lying here, so this will be theta and this will be 2 theta, but the difference of the two will be equal to 45 degrees. So here the difference is actually the addition, because one is clockwise, the other one is counterclockwise. So one will be positive, this will be positive, this will be negative. So the difference is actually the addition. So this plus this must equal to 90. This is the maximum shear stress plane. So that's why this is 2 theta. So from this you can get the 2 theta as well. Okay. So now you located the x-plane on the Mohr circle. Okay, and then you located with reference to that x-plane, you located the principal plane and the maximum shear stress plane. Now you know the principal plane and the principal stresses, and you know the maximum shear plane and the maximum shear stresses. ठीक है ना? अब आपको ये पता है. Now the next step is to calculate stresses at a certain point, at a certain plane. I'm sorry, x prime plane. Okay. So which is at an angle of theta degree with the x plane. So what will you do? You will have to rotate by an angle of 2 theta, from the x plane. आप rotate हो, if the angle is clockwise, then rotate clockwise. If the angle given is counterclockwise, then rotate counterclockwise. So here the angle given is, let's suppose, clockwise. So I rotated by a clockwise angle of 2 theta, not theta. The actual angle is theta, but I rotated by 2 theta. Okay. So when I rotated a 2 theta, I'll draw a radial line, so it will intersect the circle at this point. So this point is basically what? The x prime plane. Okay, and if you just extend it backward in a backward direction, so it will give you the y prime plane, the x prime plane and the y prime plane. Okay, so you got both the planes. Now to get the coordinate of this, one thing is that you can do it full graphically. You draw a circle to the scale and do everything graphically. Just count the square. You say one small square is equal to this one, or 1 centimeter is equal to this one, and then do conversion. Okay, and to get a particular angle, there is no need to use the sine theta. Just use a protractor or a D and then measure this angle. Okay, so it will give you the 2 theta and half it, and it will give you the value of theta. Okay, so using the same procedure, so even when you just get this point, so just measure this distance and according to the scale convert it into the normal stresses, and measure this distance, convert it according to the scale into shear stress. So you are get sigma x and tau xy graphically, not using any calculation. But since we do supplement the more circle with certain calculation, because we can do it nowadays. It's very easy. Okay, you have calculator and you can do it very easily. Okay, so it will give you what, if you want to do some calculation. So from, if let's suppose this is angle alpha, which is equal to, which you can calculate here in this case is 2 theta minus 2 theta n. Alpha is what? In this case is equal to 2 theta minus 2 theta, and both of them are known. So you will get the value of alpha. Okay, alpha is the angle. If alpha is the angle between the positive normal stress and the required plane, okay, the required plane. So if this is alpha, so you can calculate the value of this coordinate is how to calculate this coordinate, sigma x prime. This is, this one is r cos of alpha. Yahan se from this point to this point, this is r cos of alpha, because this is the cos component of r, and this is c. So you need from here up to here. So this is c plus r cos of alpha. Okay, and what about this one? This is plus minus r sin alpha. Plus minus, you will have to decide it. If it is below, take it negative. If it is above, take it positive. So you can decide it, because this is a more circle and everything will be crystal clear. Okay, so tau xy is equal to plus minus r sin alpha. Okay, and to get the coordinate of y prime plane, so y prime plane is equal to, yes, आप जरा wait करो. Hello. Hello. वालेकुम अस्सलाम. ठीक है ना? Okay, ji. So if you look to this one, so from here up to here, this is what? This is r cos alpha, and this is c, but you need this distance. So this is r cos alpha minus c, but since this is negative, so this is c minus r cos alpha. Okay, so the coordinate of this is now known to you. So these things, if alpha is the angle between the positive normal stress and the required plane, then this equation will automatically give you the stresses. Okay, automatically. But if you are using a graphical approach, everything will be according to the scale वो आपको जो है वो मिल जाएगा, ठीक है ना? You will have to just measure thing. You need not to do any kind of calculation. Okay, if you are using a fully graphical approach. Okay, so this I'm repeating this whole thing. So there are 3 slides, actually 3 big steps. In the first step, you draw the Mohr circle. So calculate center and R, select appropriate scale and draw the circle and show the salient feature like these principal plane and the principal stresses and the maximum shear stress, the coordinate corresponding to this one. The next is to locate the x plane. According to the Cartesian coordinate system, you know sigma x and you know tau x. Okay, so this is sigma x and this is according to that scale. Okay, so this and then join the center again, not with the origin, with the center of the Mohr circle extended. So you will get what? You will get the y plane. And it will automatically give you the y plane. The coordinates are known, but it will automatically give you. And then knowing the x plane, now you locate the principal plane and the maximum shear stress plane. So this is how to locate these things. Okay. And then to calculate or to determine the stress component on any plane. So if the orientation is known to you, then rotate by double of the angle. Draw a radial line at that angle, so it will give you the x prime plane. Calculate, and if you proceed, if you just extend it backward in a backward direction, so it will give you the y prime plane. And using this relation, get the coordinate of this this relation. So these are the 3 steps. Okay. Now let's do this example. Example 2.1b, view 2.1b, we already talked about example 2.1. So this is the same example, but this is also in combination with 2.2. 2.1 and 2.2 combination. To combine both of them, so we solve it analytically. Now we are going to solve it using Mohr. Okay, so for the given stress using Mohr circle method, determine principal plane and shear stresses, maximum shear plane and stresses, stress component on a plane at a clockwise angle of 30 degrees with the x plane. So this was basically our first problem, and this was related to 2.1 and these two were 2.2, and I've combined it in 2.1b. Okay, so for this state of stress, sigma x is plus 10, since this is tension, sigma y is minus 15 compression, and tau xy, you will have to look at the x plane. So on x plane it is counterclockwise, so that's why negative, and the angle is minus 30. Okay, so clockwise is important in this case. Minus and positive and negative are not important. Okay. Now your first set of calculation, your first major step, which is composed of these 3 steps, is for the given state of stress, calculate the center and radius r. So center C is sigma x plus sigma y by 2, so 10 plus minus 15 by 2 is minus 2.5. Okay, and r is, using this expression, is 17. So you got these 2 values. Okay, so now in this case, this is your sigma and tau plane. This is your origin. Locate the center, which is at a distance of 2.5 from this origin according to a certain scale. So this is 2.50, and open your compass according to the same scale equal to 70/3 and draw this circle. Okay, draw this circle. So it's very easy. Locate the center, open your compass equal to 17.3 and draw this circle. Okay. Now locate these points, write these points. So this point should be C plus R. So C is minus 2.5 and R is 17.3, so 14.8 and 0. This will be C minus R, so it will be, I'm sorry, sigma 2 is minus 19. But minus 19. and tau maximum is equal to 17.3 tau maximum, and the normal stress on the maximum shear stress plane is minus 2.5. Okay, so we got these expressions. So this is minus 2.5 and 17.3 minus 2.5 minus 17.3, and these are the principal stresses. So we got this, and this is the first set of steps to have for the motion. Okay, the next will be to locate the X plane. On the X plane, we know that the stress is 10 and minus 12. So we'll have a point on this circle whose coordinates are 10 and minus 12. So what you should do, you should from this, you just move by 10 in the positive plus 10, and then draw a vertical line so it will intersect this point. R. Move minus 12 downward and draw a horizontal line so it will intersect with this point. So both of them are, if you want to draw both the lines, so both will intersect at the circle. Okay, so if there is something, they are not intersecting, then there will be something wrong with your calculation or with you drawing the line. Okay? So you got this X whose coordinate is 10 minus 12, join this point with the center, not with the origin, center of the circle, extend it on the back side, so you will get minus 15 or comma 12. Minus 15, automatically you will get this. Again, automatically आपके पास आ जाएगा. So this will be, this is minus 15 and this is 12. Since this is plus 12, this is above, so plus 12. Okay, so you got this. Now you will have to look at the principal plane and the maximum shear stress plane. So for the principal plane, this angle is 2 theta n. This angle is 2 theta n. So sine of 2 theta n is equal to tau xy by r. देखें, sine of 2 theta n is equal to this, which is tau xy divided by r with an absolute sign. So this is 0.694. If you take the sine inverse of this is 43.9. This angle is 43.9. And theta n is 43.9 divided by 2, which is 21.90. And this angle is counterclockwise. This is automatically, you will have to rotate from the X to the required plane to the principal plane. So here it is a counterclockwise angle. So counterclockwise angle to have that is 21.9. Okay. Similarly, look at maximum shear stress plane. So maximum, you can do it like this. This is minimum side. This is 2 theta s. But if you want to move towards the maximum, so this is the maximum shear stress, which is 2 theta s. Okay, and there is no need to do calculation for this one. So 2 theta n plus 90 will directly give you this one. Okay, this is 90. And 2 theta n जो है वो you already know 43.9, so 43.9 plus 90, 133.9, and theta is equal to divided by 2, so this will give you 66.9 counterclockwise. This is also counterclockwise. And since both the angle have same sense, counterclockwise, so their difference should be equal to 45 degree. अगर आप minus कर ले इसको 66.9 minus 21.9, so it will result in 45. ठीक है, आपके पास जो है वो 45 एंगल जो है वो आ जाएगा. So now you know the X plane, you know the principal plane and the principal stresses, you know the maximum shear stress plane and the maximum shear stresses. Okay. The next thing is to calculate stresses on X prime plane, which is at an angle of 30 degree clockwise. Clockwise 30 degree पर जो है वो lie कर रहा है. So this is the X plane. You will have to rotate from this. You will have to take a D a protractor, place it here, and then mark an angle of 6 degree here, and join this with this one, so it will intersect the circle at this point. And this point is basically your X prime plane. This is what? This is your X prime plane. And if you just join this X prime plane with this one and extend it in back side, okay, so you will get the Y prime plane. Okay. Now, how to get the coordinate of this plane? So, for the coordinate, you need angle between the positive normal and the required plane, radial line with the required plane. Okay, so this angle L alpha, so since 2 theta is known to you, 2 theta n is known to you, and 2 theta is known to you, so alpha will be what? 2 theta n plus 2 theta, and forget about the sign. Okay, 43.9 and plus 60 sign is automatically, you can see the sign. Okay, so this angle is, this alpha angle is 103.9. Okay, na? 103.9. Now you can use the expression sigma x prime is equal to c plus r cos alpha, which is minus 6.66. Likewise, minus r sin alpha, जो minus 16.8 आ रहा है, और sigma है वो c minus r sin alpha, जो कि 1.6 आ रहा है. Here you can see it's very close to the tau axis. ठीक है ना? Tau axis के ये बहुत जो है वो close है. ठीक है, so you will get this state of stress. This the stress is on this plane. आपको मिल गई. ठीक है ना? You got sigma x prime and tau x prime y prime, and you got sigma y prime. And if this is minus 16.8, then it must be 16.8. ठीक है ना? So this is the way how to solve problem using Moore's second. ठीक है, आपका कोई क्वेश्चन है पूछ ले, अदरवाइज ब्रेक पे जाते हैं. ठीक है, और जो है वो फिर उसके बाद हम 15 मिनट की ब्रेक कर लेते हैं, उसके बाद फिर मिलते हैं इंशाल्लाह. ठीक है ना, फिर बाकी जो है वो कुछ प्रॉब्लम इस पे सॉल्व करेंगे. ठीक है जी. ओके, शुरू करते हैं। आवाज आ रही है मेरी आपको? ओके जी। अच्छा जी, so now coming to some problem. This is problem 929. For the state of pure, it is showing an edit. Wait for a while. Okay. So this is problem 929. For the state of pure shear shown in figure, find the stress components on planes whose normal are at plus 30 and plus 120 with x-axis. Show your answer on complete sketch of differential element. Okay, so this is a pure shear. The state of stress is a pure shear case. There is no normal component acting on this one. And it is required stress is on plane whose normal are a 30 degree and 120 degree with x-axis. So 30, the normal to the plane at 30 degrees x prime, then this 120 is basically the y prime plane. Okay, this is basically the y prime plane, or you can consider it as a plus 120 degree and do the calculation. Okay, so since we are doing it using the Mohn circle, so this is immaterial, we'll automatically get the y prime plane. Show your answer on the sketch of differential element. So you will have to draw a sketch of differential element. For this state of stress, sigma x is equal to 0, sigma y is equal to 0, term xy is 1000 minus, you will have to look to the x plane. So on the x plane, the effect is the counterclockwise, and counterclockwise is negative. When theta is plus 30 and plus 120. Okay, plus mean counterclockwise. Okay, plus mean counterclockwise. Okay. Now our first set of steps to have. So find for the given state of stress, calculate the center C and the radius R. So the center C is 0. Okay. Center C is 0. So because the normal stresses are 0. Okay. So C is 0. So it means that the center of the circle coincide with the origin. Now in this case, you can see that this is the origin and this is also the center of the circle. And R is equal to, it should be equal to the, R is equal to actually the tau maximum. So since this is the maximum shear stress, since the normal stresses are 0 or equal, so this is the R should be equal to 8000. Okay. So with this as center, since C is equal to 0, and select appropriate scale to draw this circle. And radius of the circle should be 8000. Okay. And then locate this one. So C plus R, and this should be C is 0. So this should be 8000 0, minus 8000 0, 0 8000, 0 minus 8000. So these are the cases. Now locate the x plane. How to locate the x plane? So you will have to, on the x plane, the stresses are 0 and minus 800. On the x plane, the stresses are 0 and minus 800. So which point is having coordinate 0 minus 800 is this one. This point is having coordinate 0 minus 800. So this point is what? This is your x plane. So obviously it should be the y plane. This is x plane and this is y. Okay. Now this angle, which is from the x plane to the principal plane, should be equal to 2 theta, and here it is obvious that it should be 90. But if you want to do calculation, that tie xy by r, tie xy is minus 8,000 divided by 8,000 equal to 1. So sine theta is 2 theta n is 90. So theta n will be equal to 45 degree. And the direction, this circle is giving you the direction, that the direction is counterclockwise. So the principal plane lies at an angle of 45 degree counterclockwise with the x plane. ठीक है ना, principal plane जो है वो 45 degree पर lie कर रहा है. Okay. Similarly, this 2 theta s, which is not shown here, from here up to here, from this point up to this point, so this is 2 theta s plus 90. 2 theta n plus 90, so this is 180. So theta s is at an angle of 90 degree. So obviously, the maximum shear is this one. This is the maximum shear. Okay. So this angle is 180. This is minimum shear. So the angle between minimum and maximum shear is 90. So it should be at a 90 degree. Okay. It should be at a 90 degree. So 2 theta s is equal to 180. So theta s is 90 degree. And this is the maximum shear stress plane. Now you will have to show the result, okay, of the principal plane. Show the result of the principal plane on a stress element. This is one of the requirements. Okay, so you rotate through a counterclockwise angle of 45 degree. So the stress component on this side should be 8,000 and on the opposite side should be minus 8,000. Okay, now it should be 8,000 and on the opposite side it should be minus 8,000. Okay, so this is the principal state of stress. This is the principal state of stress. And no other plane, yes, this is the principal state of stress. Now the next thing is to calculate stresses on a plane of at plus 30 and plus 120 degrees. So this angle this is your reference. This is your reference. So you will have to plus mean counterclockwise. Rotate plus 30 mean you will have to rotate in more circle by 2 theta in a 60 degree counterclockwise. So rotate by this one. So join this with this one. So this will give you x prime plane at an angle of what? At an angle of 30 degree. So this point, now if you join this point with the center and extend it backward, so you will get y prime plane. And actually this y prime plane is the plane at an angle of 120. Or 2 theta mean this angle you can see. This is 2 theta, which is 240. Okay, this is 240 degree. Again, a 240 degree angle. 240 degree. Okay, so you have this is at plus 30 plane and this is plus 120 plane. If this is x prime, this will obviously be y prime plane. Okay, now how to get the coordinate of this point? So the coordinate of this point is sigma x prime is equal to c plus r cos alpha. This is alpha, and alpha is how much? Alpha is 90 minus 2 theta, or 2 theta and minus 2 theta. 90 minus 2 theta, since this is 90, so 90 minus 60, 30 degree. Alpha is 30 degree. So c plus r cos alpha is equal to 6928. And x is minus r, minus I am writing this minus sign since this is below. So minus r sin alpha is minus 8,000 sin 30, so minus 4,000. And sigma y prime, since this is alpha, so it should be c minus r cos alpha, c is equal to 0, so this is minus 8,000, so minus 6928. Okay, minus 6928. Now this is x prime plane, so x prime is at an angle of plus 30 and a counterclockwise 30. So you rotate the element by a counterclockwise 30 degree. So this component, this is how much? This stress is 6928. This stress on the opposite, this is also 6928 but compression. And this one is minus 4,000, so it should be counterclockwise minus 4,000. So this is the stress element at 30 and at 120 degree. Okay, at 30 and 120 degree angle. So this is a complete state of stress. कोई क्वेश्चन है आपका? Okay, this is next problem, problem 935. For the element shown in figure, determine the value of sigma x and sigma y. If the principal stresses are known to be 2000 psi and minus 8000 psi. This is a state of stress in which the shear is known but sigma x and sigma y are not known. But for this point, are corresponding to this state of stress, the principal stresses are known to you. So if the principal stresses are known to you, you can draw the circle. Principal stresses are अगर आपको पता है ना, तो आप circle draw कर सकते हैं. Okay, you can draw this circle because you can calculate the value of C. So this is the case, sigma 1, sigma 2, and tau xy. Tau xy is not at the 1-2 plane. Tau xy is the x at the x in the xy direction. So sigma 1, sigma 2 are known, tau xy is known, which is plus, and sigma x and sigma y are unknown, which are required, and you will have to calculate this. Okay, so as principal stresses of the given state of stress are known, the center of radius and center and radius of the Mohr circle can be determined from C is equal to sigma 1 plus sigma 2 by 2, and R is equal to sigma 1 plus sigma 2 by 2. So C is 3000 and R is 5000. So you got now the center and you got the radius. So you can draw the circle. Yeah, you can draw the Mohr circle. So I've done it, all the things in this one step in this one Mohr circle. So I've selected the origin. Then you using appropriate scale, locate the center of the circle at it on the negative side minus 3000, and open your compass, you put 5000 this circle. Okay, draw this circle. Okay, so next is, now you draw the circle and just write the coordinate of these points. This is C plus R. So C is how much? C is minus 3000 is 5000. So it will be 2000. C minus R is minus 8000. Okay. And this is minus 3000 and R 5000 and minus 3000 C and minus R and minus 5000. Okay. Now locate the X plane on this Mohr circle, but only one coordinate is known to you. Okay, and that is 3000. So one is enough. Okay, you can do it. Okay, you can do it. You just locate 3000 here and draw a horizontal line, so you will get this point on the Mohr circle. So this is your X plane. Okay, on the X plane, 3000 is known, sigma x is not known. So you got this point, just on the same scale, you just select this 3000 and draw a horizontal line, so it will intersect the circle at this point. Okay, and join this with the center of the circle and extend it in the base or the base side, so you will get this Y plane. And on the Y plane, the stresses are sigma y is still unknown, but this should be minus 3000. Okay, since this is, if this is plus 3000, it should be minus 3000. Okay, now this is your X plane, but its coordinate are not known yet. So this angle, this is from the X to the principal, this is 2 theta n. So first calculate this 2 theta n. Okay, so 2 theta n is sine of 2 theta n is star x divided by r is equal to 0.6. So 2 theta n is 36.87. So theta n is 18.4. So you got this angle. Okay, you got this angle. Now calculate x and sigma y from Sigma x is c plus r cos of alpha. Okay, how to get the coordinate of this? If this is, let's suppose if this is alpha. Okay, so this alpha is actually to the end. So c, since this is c minus, actually it should be, this distance is how much? From here up to here, it should be r cos of 2 theta n. From here up to here, this is 1. If you subtract this c, so r cos of 2 theta n minus c, since you are opposite side, so c minus c plus r cos 2 theta n. So it will automatically see, since this is negative, so minus 3000 plus r cos of 2 theta n, so it will give you 1000. So 6, the coordinate should be 1000. You can measure it. You can measure using the scale, so it will be 1000. Okay, this one, 1000. And similarly, for the other side, sigma y is equal to minus r cos 2 theta n, r theta n. So this is minus 3000 minus 5000 cos of this. So this is minus 7000. So this is from here up to here. This is minus 7000. If you measure it, so you will get minus 7000. Okay. So you got the unknown stresses. You got the sigma x and you got sigma y. ठीक है ना, आपको वो चीजें जो है वो मिल गई, which were the requirement. ठीक है ना, वो यहाँ की जो है वो requirement थी. ठीक है ना, कि sigma x और sigma y जो है वो unknown है. ठीक है. Now this is the last problem, last but not the least. ठीक है ना, इसमें बहुत सारी चीजें हैं इस प्रॉब्लम में. There are many things in this problem, and this is problem 967. 967 problem. A 2-inch diameter bracket securely fastened to the wall as shown in the figure carries the given loads. You can see this is a bracket over to the wall firmly. Okay. And this is like it acts as a fixed support. Firmly mean it is acting as a fixed support. Okay. And this is subjected to a downward, this tip is subjected to a downward force of 800 pounds and a force in this direction of 1000 pounds. Okay. Find the maximum resulting stress at point A on the upper surface of the shaft. This is point A. Okay, this is point A, which is at a distance of 3 inches from here. From this, at a distance of 3 inches. This distance is 5 inches. Okay, so he's saying that the maximum resulting stresses at point A on the upper surface of the shaft, if the direction of the 800 pound is reversed, will the magnitude of the resultant stress at A be changed? Why or why not? क्यों चेंज होगा अगर होगा, और अगर नहीं होगा तो क्यों नहीं होगा. ठीक है ना. So this is the case. Okay, now you will have to first, this is the case of a combined stress, you will have to first, there are a number of action, there are a number of forces applied on this cross section. Okay, if you draw the free body of this one and show all the forces on this, so the forces acting on this body are like you have at this, if you just take the sum of the forces, there is no force acting in this direction. So Px should be equal to 0. Okay, Px should be equal to 0. Okay. Now, sum of the forces in the vertical direction is equal to 0. So if this is Vy, so it should be equal to 800 pounds. Okay, so Vy is 800 pounds, minus 800 pounds. Okay, Vy is in downward in the negative y direction, so that's why it is 800 pounds. Similarly, in the z direction, Vz is positive, since this is in a positive direction, so Vz is 1000 pounds. Okay, Tx is the moment about x-axis, about this axis. So this moment is caused by this load, because this is perpendicular. This is caused bending in this one. This is not caused any rotation of this member. This is caused twisting of the member at arc about x-axis. So 8000 into 5. So this is 4,000 pound inch. Okay, My, moment caused about y-axis. So this force is also causing moment about y-axis also. Okay, I'm sorry. This one, this 1000 is causing moment about y-axis. So, and since we'll talk about this negative sign, so 1000 into 3 is 3000. So why I'm giving, why I'm writing this negative sign? So this negative sign is if you rotate your finger, basically this load will cause compression on this side and tension on this side. If you press your finger on the compression phase, this is the compression phase, or this is the compression phase. Okay, so if you press your finger, the finger of your right hand on the compression phase, your thumb will be in the direction of moment vector, and this is the moment vector. This is the moment vector. This is the compression phase, so this is the moment vector. So that's why, since this is in the negative y direction, so I'm writing it as a negative number. So minus 3000 pound-inch. Okay, this 8000 it is also bending this member. It is also cause bending or moment about z-axis. This is z-axis, so 8000 into 800 into 3, and this is also according to the sign convention. If you just look to this load is causing tension in the top fiber and compression in the bottom fiber. And if you just press your finger on the compression phase, this is the compression phase, so your thumb will point in this direction, which is a negative z-axis. So this is a positive, this is a positive axis, this is negative, so that's why mz is also negative. Okay, so you got the forces. These are 6 forces acting on this member. There is only one zero force, which is px equal to 0. All other forces are non-zero. Geometric properties. Area pi d square by 4, which is 3.141. Iy is equal to Iz, the moment of inertia about this axis, pi d power 4 by 64, which is 0.785. And J, which is the polar moment of inertia, or the moment of inertia about x-axis, which is pi d power 4 by 32, which is 1.571. Okay. Now the normal stresses at A are given by this moment, and this moment can cause stresses at A. Okay. But moment about y-axis will not cause any stress at A. Moment about y-axis will not cause any stress at A because its distance is 0. So just plug in the value and it will automatically give you, so sigma x is equal to px over A minus mz over iz into y. There is a negative sign here but a positive sign here. So px is 0 minus pmz is minus 24,000, 0.785 plus 1. So this is mz and this distance is plus 1. The total diameter is 2 inches written here. Okay, so it should be 1 inch. So this will give you 1, and this is my divided by iy into my divided by iy into this distance is 0, because from the y-axis the distance, the z is 0. This is the point. We want to calculate stresses at this point. Okay, so this is 0, so the stresses is caused only by this mz, which is equal to 3057. Okay, so the normal stress at point A is equal to what? Is equal to 3057. Now the shear stress, for the shear stress, so there are basically this Vy is causing no stress at point A. Why? Because this point is at the surface. If you draw on the vertical plane, if you draw the stress variation diagram, so if this is our y-axis, this is the depth. Along the depth of the stress variation is like this. This is the stress variation line. Okay, so since the point lies at the top, so Vy is causing no stresses at A. A पर वो कोई stress cause नहीं कर रहा, because at the top the stress is 0. The shear stress, this is the shear stress variation diagram. Shear stress is maximum at the for a circle section at the centroid, at the neutral axis. Okay, at the centroidal axis, and 0 at the top and bottom. Okay, 0 at the top and bottom. So Vy is no more there. We are dealing with point A. Okay. Now, other two forces, the shear stresses are caused by three forces: Vy, Vz, and tau x, Tx. You can have Vy, Vz, and Tx. So Vy, तो बीच में से निकल गया. So the no stress is caused by Vy. So there are two forces, Vz and Tx. Okay. So first we'll talk about the stresses caused by Vz. Okay. The stress is caused by Vz at A. So along this line, a uniform stress is caused by this Vz. Okay. And how to calculate that stress? Along this line, a uniform stress is caused by this Vz. Okay. And how to calculate that? So we can calculate Qy is equal to Ay bar. This is the first moment of area. Okay. And since we want to calculate stresses at this location, so I'll have to take area to one side of this. So I'm taking this area. So area here is half of the circle. So pi d square by 8, which is half circle area. And this distance for the half circular centroid is located as a 2d divided by 3 pi. D is the diameter of this circle. So 2d divided by 3 pi, this centroid is located here. So if you simplify this one, so d cubed by 12. So this is d is 2 cubed by 12, which is 0.667 inch cubed. Okay. Now the shear stress tau xz is equal to Vz, Qy, Iy, By. So Vz we know from the previous slide, Vz is 1,000 pound. 1,000 pound into Qy we calculate 0.667. Iy from the previous slide, Iy is equal to 0.785. And B is this one. From here up to here, this is B. The width at the location, what is the width at that location, which is B. So it will result in 427 psi. Okay. So if the force is acting in this direction, stresses will be in the opposite direction. Okay. So this is one thing. The next is the stresses caused at A due to Tx are given by tau x is equal to Tx rho divided by J. And since this point A lies at the extreme, okay, so for the maximum, the expression is 16T divided by pi d cube. If you plug in rho equal to d by t and J equal to pi d power 4 by 32, so it will result in this one. Okay, so 16T divided by pi d cube. So this is the maximum stress. So 16 into Tx divided by pi d cube. So 2546 psi. Okay. Now since the torque is acting in this direction in a counterclockwise, so its resistance should cause a clockwise moment. Okay. So it should be the stresses direction should be like this. This is the stress variation. So the stress variation is a triangular variation. Okay. So at point A, the stresses are 2546. Okay. Now, if you look to the stress direction here is to the right and here is also to the right. So both are in the same direction. So tau xz is equal to 427 plus 2546 is equal to 2973. So now you got stresses. One is the normal component and the other one is the tau xz. This is in the xz direction. Okay, the stresses are caused in a z direction on an x plane. This plane is what? This is x plane, okay, because its perpendicular is the x-axis. This is the plane and its perpendicular is x-axis. So the state of stress is this one. I've shown it like this is the x-axis and this is my z-axis. Okay, now this is x-axis, this is my z-axis. On the x-axis, the stress is the normal is 3057 and the shear is what? The shear is 2973. Okay, the shear is 2973. So I can now calculate CNR for the Mohr circle. So CNR is sigma x plus sigma z by 2. So 1528. R is equal to this one, which is 3343. If you calculate it, okay. Then using appropriates, locate the center and draw Mohr circle. So this is locate the center 1528 and draw the Mohr circle. Okay. So you will get and get the coordinate of this 4871 minus 1815 and this one is 1523 and 3343 and this is 1528 and minus 3343. Now locate the x plane, and x plane is this one. Okay, this is x plane. On x plane, the normal is 3057 and the shear is plus 2973. Okay, so how can you do this? You can, normal is from here up to here, just measure a distance of 3057 and draw a vertical line, it will intersect here. Okay, or from here up to here, just measure a distance of 2973. Okay, and then draw a horizontal line, so you will get this one. Okay, so if you join this point with this one and extend it, you should get, it should intersect it at this point. Okay, exactly at the intersection of this with this, so that the normal is 0 at this point, because we know that the exact axis the normal is 0. ठीक है ना, ये हमें पता है कि normal जो है वो यहाँ पर 0 है. ठीक है ना. So these are the this is your reference, this is your x plane, this is your y plane, and then you can calculate this 2 theta n x or maximum के बीच में this 2 theta n from the trigonometric relation. You can calculate this. So which is not required in this case. He's saying that just calculate the maximum stresses at that location, and you calculate the maximum stresses. And the maximum stress is 4871 and minus 1815, and the shear maximum is 3343. Okay. Now he is in one of the statement, the last statement, he is saying if you reverse the direction of the 800-pound force, like if we reverse this force, what will happen? When we reverse this force, so what will happen? The direction of the torque will get reversed. Direction of the torque जो है वो reverse हो जाएगा. So जब direction of the torque reverse हो जाएगा, so what will happen? It will not reverse because this is a VZ, which is this one, but it will reverse its direction. Like if you make it like this, so it will reverse. This positive side will be negative side, and this negative side will be positive. So what will happen? Then at A, both stresses will not be added to each other. Rather, it should be 427 minus 2546. Okay? So you will get a negative and lesser stress at point A. Okay, so I've written it. I haven't done the calculation, but when the 800-pound load is reversed, normal stresses will not change, but direction of the torque and therefore shear stresses will change. ठीक है ना, जब टॉर्क चेंज हो जाएगा डायरेक्शन, तो shear stresses जो है वो ऑटोमेटिकली चेंज हो जाएंगी. आपके पास जो है वो 427 माइनस 2546 हो जाएगा, सो माइनस 2119. तो अब ये जो है वो 2973 नहीं होगा बल्कि 2119 हो जाएगा. सो इट विल ऑटोमेटिकली चेंज द होल स्टोरी एंड द स्ट्रेसेस विल बी नॉट इक्वल टू दिस वन, इट विल आल्सो चेंज. ओके, last slide of today's lecture is some common state of stress. Some common state of stress. One is pure shear. So we already discussed a case of pure shear. So the case of pure shear, in the case of pure shear, the center of the circle coincide with the origin. Okay, and if this is the pure shear, then the corresponding normal stresses are also equal in magnitude to the pure shear. Let's suppose if tau is 100, then the principal stress will also be equal to 100. Because this is equal to, if this is tau, then this is also tau. Okay, and this is minus tau. Okay. Now this is a state of stress where sigma 1 is sigma and sigma 2 is minus sigma. Okay, so this state of stress is equivalent to this state of stress. Now, here you can see that if you have a principle of plus sigma and minus sigma, then the shear is also plus sigma and minus sigma, same as this case. Okay, so this is equivalent to this one if sigma is equivalent to tau. ठीक है ना? So ये आपके पास ये तो एक चीज जो है वो हो जाएगी. For uniaxial state of stress, where sigma 2 is equal to 0, uniaxial state of stress. So this is the Mohr circle. Okay, this is the Mohr circle, and this is the X plane. Okay, so if this is sigma, so its coordinate is sigma by 2 and sigma by 2, sigma by 2 minus sigma by 2, and this point is having 0 coordinate. Okay, so this is the maximum shear per your normal maximum shear plane. On the maximum shear plane, the normal and the shear component both will be equal to each other. Okay, so this is the most important state of stress in which sigma 1 is equal to sigma 2. And if sigma 1 is sigma, then sigma 2 is also sigma. Yeah. And this kind of a state of stress is known as a hydrostatic state of stress. Hydrostatic meaning that the stresses are equal in all directions. In the case of a water pressure, if you just place a body inside a water, and if you take a point within that body, so or if you take a small element inside a body, so the pressure from all sides within on that body will be same. Okay, so hydrostatic, since this is similar to the water pressure, which is same in all directions, so the name hydrostatic is given to this one. So hydrostatic state of stress is this state of stress. So for this state of stress, if you calculate C, so it will be sigma plus sigma by 2, so equal to sigma. So this is sigma 0, this is the center point. But if you calculate R, so it will result in 0. What does it mean? So if R is 0, then there is no circle. Okay, and there is no circle. Okay, so how can then you transform stresses from one plane to another plane? So if you rotate inside a point, the circle is a point now. It is a circle of 0 radius. You can say it like this. It is a circle of 0 radius. If you rotate inside a point, you will remain in the point. Point से तो आप change तो नहीं होंगे ना, आप उसी point पर रहेंगे. So in the case of a hydrostatic state of stress, if you rotate to any orientation, the stresses will remain constant, same. The stresses will be sigma 1 will be sigma and sigma 2 will be sigma in any orientation. If you calculate in this direction, in this direction, in this direction, in this direction, in any direction, the stress will be same. Okay, and there will be no shear stress in this state of stress. No shear stress. Okay, in any plane, if you rotate to any plane, there will be no shear stress. Okay, no shear stress induced in this case. So these are some common state of stress, and this is the end of today's lecture. If you have any question, you can ask question so that we can wind up today's class. कोई क्वेश्चन है आपका? अच्छा जी, this stress transformation is the easiest lecture of mechanics of solid 2. सबसे easy है, ठीक है ना? Because it involves some equation and some well-defined procedure. Okay, but you will have to, if you can do one analytical problem, you can do all of it. If you can do one more circle problem, you can do all the problem. Okay, there is no big issue. The only thing is in the calculation of forces. Okay, sometimes the state of stress is not directly given to you. Okay, so that could be a problem for you, but for the other cases where the state of stress is given to you, so it's a very straightforward, but you will have to do it, and you will have to give it at least 2-3 hours. Just listen to this lecture in a fast mode, okay, and then try to read your book and try to solve a few questions, 2-3 questions, 4 questions you have on this, and you are finished. You will learn each and everything regarding this Mohr circle. And I will recommend that you draw a Mohr circle on a graph paper yourself, proper जो है वो graph paper पर आप जो है इसको draw करें. ठीक है जी? कोई question है आपका? Okay जी.
No sir.
जी पूछें. No question. Okay.